So we're going to look at the transformation of exponential functions. So of course, now that we know how to graph a basic exponential function, we're going to look at applying our understanding of transformations to now exponential functions. So hopefully this won't be too bad. I'll make it as simple as possible, but we have already studied transformations of other functions previous to this. So this should be a little bit of review and maybe not too difficult to learn. So remember things with these equations when we transform a certain function. This c value at the back is usually our value if we're going to move up or down. So that's our vertical translation. Remember to change this sign, but that is our d value here is our horizontal translation. We have vertical stretches and compressions out here. And then we have horizontal stretches and compressions, but remember that we always multiply by the reciprocal. So that's another tricky one. So previously we have looked at this equation before and we've understood some of the transformations. Slight difference now. We might have different base functions. So for example, b to the x is going to be our base or our root function. But the base here, the value for b could be different. So if we have 2 to the x, that would be our base function. If we had 3 to the x, that would be our base function. So it all depends on what the base is of your exponential function. So exponential functions, maybe it has a slightly different look to it. This is still our vertical stretch or compression. We still have horizontal translations, but look at it, it's in the exponent now. So that's a little different. And the vertical translation is still at the back, just like it was before. But our horizontal stretch or compression, which we use the reciprocal, is up in the exponent. So remember, I'm going to go over a couple of times today about how this x needs to be isolated on its own so that we actually understand the true k value and also what our horizontal translation number is for d. So down below it says you may need to factor the exponent to see what the true transformations are. For example, if your exponent is 2x plus 2, remember that that is not a horizontal translation left 2. We'd actually have to factor out the 2 first. So I see that this is my horizontal compression by a factor of a half, and I'm actually going to go left 1. So we have to be careful about always having our horizontal translation as just x so that we can clearly see what that value is. Another important note is that some exponential functions can be written using different bases. So for example, if you saw something like g of x equals 16 to the x, so this would be our base function. One thing that I want you to know is that 16 is also the same thing as 2 to the 4th. So 2 to the 4th is the same thing as 16 and the exponent is still x. Those are the same value. So I could write that then, since I know that I multiply exponents when I have a power of a power, I end up with 2 to the 4x, and that is actually the same function. But maybe this would be a little bit easier to graph when the base is only 2. So when we look at an exponential function to graph, I would like to always think about what is the base first. So the base function, if I see 3 here as my base, then my base function would be 3 to the x. So when I think about my table, I'm going to always make a chart because that seems to help a lot. And when I do make my chart, the first thing I want to look at are the ordered pairs for that base function. This also means that I'm going to go left 1 and down 4. So I'm going to try and make this as easy as I can. Maybe I would just pick some x values that are close to 0, -2, -1, 0, 1, 2. We don't need much more than that. And then to figure out what my y values are, 3 to the exponent -2. So 3 to the -2 means 1 over 3 squared. So that would be 1/9, just using some of our exponent rules. And then 3 to the negative 1 is actually the same thing as 1/3. 3 to the 0 is 1. So there's our interesting characteristic. It doesn't matter what the base is, anything to the power of 0 is 1. So that's a very common point to get. And then 1, so if I sub in a 1 up here, 3 to the exponent 1 is 3, and 3 squared is 9. So there's my original base function and the ordered pairs that go with it. What I need to do, and some of these I might end up just writing decimals. I'm not going to worry too much about these fractions. Graphing 1/9 on a graph, like we're just trying to be as accurate as we can. But what my translation tells me here is that I'm going to have to subtract 1 from my x, and I'm also going to have to subtract 4 from y. So subtracting 1 from x isn't bad. Subtracting 4 from y, like I said, I might just use some decimals here. I could use common denominators, so 1/9 minus 4 would be the same thing as 1/9 minus 36 over 9, which would give us negative 35 over 9. If you really wanted a fraction, but I think long ago I might just do 1 divided by 9 equals and then subtract 4, because a decimal is okay for this, because I mean negative 3.9 on the graph is going to be a little hard to show anyway. And the rest I would follow the same. So 1/3 minus 4, I got if I round it off, about negative 3.7. If I do 1 minus 4, that's a little better. That's just negative 3. 3 minus 4 is negative 1. And 9 minus 4 is 5. So I have my new set of ordered pairs. Something else I usually like to picture is I like to imagine what this base function looks like. What's happening here is that this is an increasing exponential function. So it's going up from left to right. I'm only going to move it left 1 and down 4, so you can kind of imagine it might look something like this. So I know the picture of what it should look like. So I just do my best to sketch my function. It is increasing. It has moved left 1 and down 4 from my original base function of 3 to the x. I also want to state the domain and range. So since this function will continue to go all the way to the right eventually and all the way to the left, my domain is the set of x such that x is an element of all real numbers. And my range, well, the range vertically is anything above negative 4, but it's not ever equal to negative 4, because it's never, this is our asymptote here. Our function is never going to touch this line. So the set of y such that y is anything greater than negative 4, and y is an element of all real numbers. And if we had to state what our asymptote is, the equation of our horizontal asymptote is at y equals negative 4. So I'm looking here and I see that I do have a stretch value out front, a vertical stretch. My base function here is 1/2 to the x, so be careful with that. And sometimes I like to think about what this might look like when I'm done. So if I have 1/2 to the x as my base function, I know that that graph is going to be decreasing because I have a fraction here as my base. So this from left to right is a decreasing exponential function. But then I do have a reflection in the x-axis. So I know if this is reflected vertically in the x-axis, it's going to look something like that. I also do stretch it, and I also move it right 4 and up 5. So maybe it's going to be something like that, but over here. I guess I just like to know the general shape, and once I'm done if I did get it in an accurate position. So again, I'm just going to use values that are close to the origin, like negative 2, negative 1, 0, 1, 2. When I sub in a negative 2 here for x, 1/2 to the exponent negative 2 would be 2 over 1 squared. So I actually get 4. When I sub in a negative 1, that's 2 over 1 to the exponent 1, which is just 2. When I sub in a 0, again, that's our special point, because anything to the 0 is 1. And if I sub in a 1, I get 1/2 and 1/4. So now I need to decide what I want to do first. So it looks like I don't have a horizontal stretch or compression. I do have a vertical stretch, and the y values would also have to be multiplied by -1. So in the end, I need to start by multiplying my y values by -2. So remember, your x values stay the same. My y values were all multiplied by -2. Then I can do the rest here. I can add 4 to my x and add 5 to my y. I also can imagine that if I'm moving this graph up 5, that my asymptote will be at y = 5. And we just do a sketch as best we can to make it look like a curve. It does look similar to what I was imagining, and it's in the right sort of position. My domain is always a set of real numbers. The range is anything less than 5, so y such that y is less than 5. And the equation of the asymptote is where y = 5. The next one is important to point out what we see as the exponent. So first, our base function is 4 to the x. I need to work on this equation first before I begin though, because I need to factor out the -2 that I see in the exponent. So it looks like x plus, because -4 divided by -2 is 2 plus 3. So now we see clearly that we go left 2, up 3, and we do have a horizontal compression by a factor of 1/2. We can also notice that we do have a reflection in the y-axis as well. So if I can imagine what this looks like first, I had a base of 4, so I had an increasing exponential function, and then I am going to reflect it in the y-axis, so it's going to end up looking like this. As well, it's going to move left 2 and up 3, so it's sort of this shape up here. Using the same x values just to figure out where my base function would be, 4 to the -2 is the same thing as 1/4 squared, so that would be 1/16. 4 to the -1 is the same thing as 1/4. 4 to the 0 again is 1, and then 4 to the 1 is 4, and 4 squared is 16. Some of these points you may not be able to fit on your graph, and that's okay. If there's ever a point that doesn't fit on the graph paper, you could just leave it off. The next thing we need to do is multiply our x values by -1/2. After that, we can apply our horizontal translation, so we'd have to subtract 2 from x and add 3 to y. I might just leave these as fractions, adding 3 to 1/16. I would just maybe write 3 and 1/16. Obviously, that's going to be pretty tricky to graph. It's like 3 and a tiny little bit, 3 and 1/4. You can kind of imagine what that would look like. 4, 7, and 19. Again, 19, I don't think I'm going to be able to fit on my graph, so I'll just leave that point off. I also know my asymptote. Horizontal asymptote will be at y = 3. And there were a lot of decimals in this, this particular graph, but we just do our best to show the location of that exponential function. Our domain is just the set of x such that x is an element of all real numbers, because we go all the way horizontally from side to side. The range is anything greater than 3, because this is above the asymptote, and our horizontal asymptote is at the line y = 3. I just wanted to mention the homework. There is a homework question, I think it's number 10, and this is the function that you're given. I wanted to just make a special note here. 1/2 x plus 3 is the exponent. And again, I just want to point out, this exponent, you cannot leave a fraction right beside the x. I need to clearly see what my horizontal translation is, and I need this x to be on its own. So I need to factor that exponent. Just be careful with this one. If I factor out a half, think about 3 divided by a half. How many halves go into 3? So I'd actually end up with plus 6. I thought that was extra difficult. This means I do have a horizontal stretch by a factor of 2, and I'm going to go left 6. There's also something a little special in example 4 that I'd like to point out. So 9 to the exponent x, those would be some pretty large values to be able to graph. So what I'd like to do is, instead of leaving the function written in that way, 9 is the same thing as 3 squared to the x minus 4. That is the exact same thing. And that's the same thing as 3 to the 2x minus 4. So I would rather see, when I have a large base like that, if I'm able to write it with a smaller base, sometimes that makes my work a little easier. I'm going to say now that the base function is actually f of x equals 3 to the x as my base function, which might be a little bit easier to start. Then I'm going to have a horizontal compression by a half. I'm not going to move anywhere side to side, but I am going to move down 4. So the first thing I need to do is I need to multiply my x values by a half. What I would need to do next is just make sure I subtract 4 from my y's. So maybe making this a decimal and then subtracting 4, I got negative 3.9, negative 3.7, and then the rest weren't as bad. I also see that my asymptote is at y equals negative 4. Before I go further with my graph, I can kind of imagine what this looks like. So I know my base function would be increasing because it was a base of 3. And then I do move this, I know that I do compress it by a half, but I do move it down 4. So it might be a little bit more steep, but down lower, just so I make sure that I'm getting it in the right location. So my curve ends up looking something like that. My domain is the set of all real numbers. The range has to be anything greater than negative 4. And the equation of the asymptote, the horizontal asymptote, would be y equals negative 4. So the last example, if we were just given information about an equation, would be able to write the equation. So a function with a base of 2, so I know that my base function is 2 to the x. It's been stretched vertically by a factor of 1.5, and it's also been reflected in the y-axis. So if it's been stretched vertically by 1.5, and when it is reflected in the y-axis, my exponent would have a negative in that case. And also the asymptote is the line y equals 2. So this has moved up 2. The y-intercept is 0, 3 decimal 5. So let's check that. If x is 0, what do we get? We get 2 to the negative 0, which is just 0. So I get 2 to the 0 is 1, so I have 1.5 plus 2, so I actually do get 3.5. And that's what it said. The y-intercept is supposed to be 0, 3 decimal 5. So I think, yes, we must have the right equation. What this would look like is that we have an asymptote through y equals 2. And our exponential function would be increasing because our base is 2, so it kind of would look something like that. However, we do have to double check that we have a reflection in the y-axis, so our final function would end up looking kind of like that. So our domain is still the set of real numbers, and our range would be anything greater than 2.